So, my name's Don Sims, and I am president of Lee and Sims. Why am I president? Because I'm the tallest and best looking, and I have the most hair. Actually, we flipped for it and I lost. So, that's why I'm president, but I'm up here just to give a brief introduction, kind of history of how our little company came to be and how we ended up here. Our company was started by our father, who's pictured here. This picture, we don't know the date, but the license plate on the drill rig said 1958, so we're assuming it's somewhere around there. So he's been in drilling business his whole life, and he was your typical 50s greaser with the cigarettes rolled up in his white t-shirt, and he was into fast cars. And so he kind of made his name for himself. Here's a picture from 1960 with his dragster. And actually, any of y'all that are into drag racing, there's Don Garlitz has a museum down in Ocala, Florida, and our dad's car is actually in that museum. He was kind of a trailblazer in the late 50s and early 60s, and this little inscription said, "This chassis is the first one to break the 160-mile-an-hour barrier in the quarter mile," and he was the first to run nitromethane in a car anywhere in this area. Kind of Don Garlitz was the granddaddy, as you know, and he helped him get into that, and so he was kind of trailblazer. You know, that most of the big breakthroughs were happening on the West Coast, but he made a name for himself here on the East Coast. And just a little side note on our father. Anyway, this company was started in 1985 when a man named Wendell Lee gave my dad $50,000 to buy himself a rig like this. At the time, he had already been in the business of 30 years, trying to figure out any way to drill a hole with a machine like this. And he used this when he first started this company, primarily drilling shallow groundwater. And he used the rig to basically drill any kind of hole, foundations, recovery wells, dewater wells. So he gained a lot of experience in that area. And in 1988, somehow he convinced my brother John to come to work for him. And so Johnny went to work in 88 as a hand on the machine, and soon thereafter they bought a top drive air rotor rig. This is not the one. This is one we purchased in 2007. I couldn't find a picture of the 1988 version. But anyway, this allowed them to drill deep bedrock wells and deep recovery wells. And I put this up here just because it's a funny picture. It shows my brother's nice legs. Him and my dad standing next to a brand new shiny 12-inch hammer with a 15-inch bit. And one of the niche markets they found was drilling elevator shafts. And they got in with the Dover elevator, and they used the old bore machine and the bucket auger rig I just showed you to drill the ones provided we didn't run into rock. But if you know this area, a lot of times rock is shallow, and they need to go much deeper. They have to use an air handler. That's what this was originally purchased for. Also found this to be used for drilling bedrock holes to set piles in for. I know they did some work down on the Georgia football stadium in Athens, and some other work in that area. And here's a picture of, that's my brother John up there operating the rig. And for any of y'all know anything about our company, know Kyle Wilson? That's Kyle Wilson as a young man. Doesn't look anything like that anymore, but he still works for us. And this was actually drilling for a recovery well on an environmental site sometime in the late 90s, I suppose. Anyway, in 1997, I was working up here for engineering consulting services, and my dad convinced me to come to work for him, and, that's how I ended up there. Matter of fact, Scott Marshall was in here, working in the same office as him back in 1997 when I left. But shortly thereafter, in the early 2000s, we kept getting a lot of requests to do foundation holes, and there was only so much we could do with that old bucket auger rig, and so in 2003, we purchased this machine, this INT 180. It's actually still working today, so that's kind of how we got our start. And it's grown since then, and as you'll see, as my brother comes to present this case study on the Harbor River project, we've grown quite a bit since then, and we've got a lot more sophisticated in the work we've done. And one interesting thing about our company, I think, is that not only have we never hired anybody that had any foundation drilling experience before they came to work for us, I don't think we've ever hired anybody that had any drilling experience at all. So it's all homegrown, and we kind of all figured it out on our own. I attribute most to my brother, John. He kind of figured it out and kind of made us what we are. And I just kind of went on to his coattails. So here he is.
All right, so Don told you saw the pictures. Tried to clean my fingernails last night. They're still dirty, but I'm more comfortable in a pair of work boots than on the job site. I've never been an office guy. I don't claim to be. And Don's very good at that. He takes care of that for me. Thank goodness. I enjoy being on the job site, working with guys and equipment. This presentation, I'm sorry you're getting right after lunch. I'm obviously not a professional presenter. I don't do this often. I'm very uncomfortable here. It's all Jeff Harms's fault. That's Jeff in the back.
What good time for you to walk in?
Yeah. So, blame it on Jeff. When he told me this 3 months ago, it sounded like a good idea because it was a long way, but then we got closer. I was really regretting that decision, but anyway, we're gonna talk a little bit about the Harbor River project today, and we're not gonna talk a whole lot about the filling part of it, but there's some things I think you guys would be interested in hearing about, some of the things that took place there that would be relevant to what's going on in the industry today. And you can see there, that picture was taken by Don's son, Joshua, as we were finishing the job. You can kind of see our hotel, and you can see it was a pretty nice setup compared to coming from a bucket on the rig. When I started, I never dreamed that Lee and Sims or we would ever own equipment like that. So we've been blessed. Thank the good Lord for that. Thank the opportunity to share this today. So the project is US 21 over Harbor River. It's near Beaufort, South Carolina. It's there's another picture. If you'll notice from this picture, it's all green. But the Harbor River opens out into the Atlantic Ocean, facing directly northeast. And so one thing we did realize was there's no protection there. That's a very windy place. We had northeast winds, which in the winter, when the production went on, that was a prevalent winds out of the northeast, so it's quite windy. So the job consisted of replacing this old swing span bridge. You guys been to Fripp or Honey Island, or been across that old bridge? If you ever drove that bridge, you know that it's a harrowing experience. I think it was 9-foot travel lanes, no curb. You can see the swing bridge opening there. While we were working on the job, it wasn't uncommon to hear mirrors breaking and people with campers. It is very narrow and tricky to get out there, and it's the only access was on this 80-year-old bridge, and maybe it's out to Harbor Island, Hunting and Fripp Islands. And the bridge was in pretty bad repair. It's 80 years old, and there's no had the old rivet steel swing section, which you could actually see through a lot of the steel was so rusted. It was outdated and needed to be replaced. This picture, you can see that's part of the new production. It's over the channel there. You can see the difference in the two structures. What an improvement the new bridge is as far as getting access. It being the only access, of course, there are a lot of houses at Fripp Island, a lot of expensive houses. That's a big beachfront community. And then the state park out there. So just for the people to get building materials, concrete, anything out there over this bridge was a little bit of trouble. So, the DOT put this job out. Michael Baker did the initial, design for, enough to get the design build project out there. Called for 3,340 foot long bridge with a 65 foot minimum vertical clearance high tide and then 90 foot horizontal clearance in the channel. Two 12 foot wide travel lanes, 10 foot paved shoulders on each side. The part that we were involved in was the drill shafts, which are just in the channel. There's a total of 18 of those, 105 to 115 feet deep, 8 foot diameter. Goes on to say when we constructed it, and the bridge actually opened in April of 2021. So here's the part I'm gonna be kind of like I always want to be a NASCAR driver, win a race, give all my sponsors here the word. I needed all those stickers on my shirt. This group, we all do this for a living. You know, we work with good groups and bad groups, and sometimes things are kind of hard, but this was a really, really good group. Everybody involved helped make this a really successful project. The contract was awarded to United Infrastructure Group, and Billy Hartley headed that up. They were really good to work with. United hired Kaiser Infrastructure Consulting and Engineering to do the final design. So they were designed as geotechnical engineers and also involved in construction. The DOT, of course, wrote the checks, very important. KB International, I want to give them a shout out, because we're going to talk about that in a minute, but any of you that work in North Carolina know that every set of slurry plans say only metal construction allowed. They don't allow any polymer construction. We were able to get it approved for this project, and a big part of that was KB International. They didn't make any money on this job. They put a lot of hours into making this happen, working with the DOT and assuring them and getting this done. SME, David's gonna speak when I get to the end and talk about testing on the shafts and the mass bore. But David was out there a lot. SME was doing the CSL and the thermal testing. Michael Baker International was hired by the DOT to act as the DOT, and they were really, really good guys to work with. So they were overseeing construction, making sure we followed all the rules, built it like it's supposed to be, and then, of course, the environmental concerns. GRL was involved with the test shaft. Once again, we went through a lot of revisions on the O-cell shaft in order to meet the requirements of the mass fluid and those type of things. So they had to do a lot of work there, and they were good to work with. Running on concrete, scheduling on this job, Brett will tell you, was a big deal. Because the access I'll show you later, but Brundage and Low Country did a good job of being there when we needed them, even by training schedule changes, and then Brett had to deal with the same thing. They did us a good job. Casings out there, we had the issue of the access and the timing of deliveries, and I'll show you about the delays later, but I think Brett ended up with all these huge cases blocking his yard for months while we went through the permit delay. So we appreciate them working with us on that. So the foundation design is completed. Required indents 1 to 21, those run a trillion steel pile. Excuse me, interior vents 2 through 7 and 17 through 20, which I think you can see those with the square pile caps on them. Those were groups of 5 or 6 24-inch concrete piles that were driven. They were probably 100 to 115 feet long with those very large pile caps and a lot of steel in them, and then the columns. And then the part we were involved with was bins 8 to 16, which here is the drill shafts that just have the columns in, and all the ones over the channel had the big strut support on top of the shafts as well, and they were a little bit deeper at 115 feet. So the test shaft, when we originally were told we had the contract to do this, one good thing about it being design build was there was a lot of lead time. So I don't know, we had a year or so, I guess, to get ready for this. And we looked at, this is the drill shaft actually location somewhere right in here. This is out near between the end and vent 1. The actual actual production shafts are in this area of the channel, but, for the test shaft, we had this temporary permit. But we had talked about this, we talked with the mineral slurry providers, we were very concerned about the saltwater, possible contamination of the slurry. If you guys mess with mineral slurry, you know, you can get flocculation from salt, we have a lot of problems, and the way you resolve those problems is with things that the DOT wouldn't want, especially in an environmental sensitive area like this. The other issue was, of course, the desanding of the slurry. You can see how far this is. The access road, how we're gonna handle the desanding area along with the environmental concerns, which there was, anytime you're in an area like this, you guys that do this for a living know that environmental is a big part of the project, and they don't wanna shovel full of anything in the water. And we also have the tide of 6 to 9 feet, so there's a lot of current out in that channel. About 12 miles an hour, I think, was the speed of the current in the channel. So we were concerned about things getting away, washing, and also, this is a very visible area. So if you look at that old bridge, there's a lot of traffic back and forth from those islands. So if you spill something, somebody's gonna know, and you're gonna have trouble. So we decided to attempt to get South Carolina to approve power slurry for this project, primarily for the desanding operation and then the salt water. Like I said, South Carolina does not allow mineral slurry. I think they had trouble many years ago, and they've just banned it from use. And so getting it approved was not an easy process. That actually took several months. I think, if I remember right, it was like 300 pages of documentation that we sent in and KD sent in. Luckily, it was design build, so ICE was involved. Michael Valakat, Joe Bailey. You know, Michael Valakat used to be in the NCDOT in the coastal area. And so he was very, very familiar with polymer slurry, and they actually preferred polymer slurry based on skin friction gain, hopefully. So we had them on our side, and they also did a lot of legwork in getting this approved. So it took several months, but finally, we were able to get the DOT to approve the use of polymer slurry on the project. The other thing that was unique in this project was mass pours. Anybody out here, did y'all cool any shafts? Any of y'all done that yet? So we had it. We didn't know what that entailed. We had put that on UIG to figure that out, but we had to deal with it. And so when we originally took the project, we all were under the assumption it would be like one central cooling tube in the center of the shaft. And that wasn't gonna be too hard. We're gonna pump some cool water, we're gonna cool this shaft, and, well, that's not what happened. So the engineers got involved, they were way smarter than me, and determined that what we'd have to do to cool these shafts would require multiple cooling tubes. And they came up with a configuration of 6 cooling tubes in a 24-inch circle, which that turned into another problem. Now we gotta figure out how to pick this thing up and get all this stuff tied in. There was a lot of stuff. I didn't have anyone to ask. We'd never done this before, and didn't know anyone who had done it. So we were doing a lot of this planning, hoping this stuff would work. And so I thought you guys might be interested in some of that. That's why David's gonna speak a little bit and talk about how all that turned out. The other problem was concrete. It's like an hour and 15 minutes to the nearest batch plant, which is up at the marine base on the other side of Beaufort. It's a long ride down there. And UIG and Low Country Concrete determined they wouldn't be able to supply from there, so we ended up putting a temporary batch plant on the laydown yard about 3 miles away. As I was saying before, the permit for the test shaft was just a temporary permit. It didn't give us very much room at all to work with this, with the large cage. And we had to come up with a lifting plan. So once we determined what the cooling system was gonna look like, we had to figure out how to lift this. You guys have lifted those cells before, you know it's always kind of tricky lifting those things with the heavy cell and the steel. The weight of the cage is in the 75,000-pound range. It's the South Carolina deal with the seismic design, so there's a lot of steel, a lot of hoops, double hoops, triple bars, and then we had the cooling tubes that had to go in there as well. So we decided we would not be able to lift that traditionally with running blocks and multiple peak points, and we wouldn't be able to keep them distorting that cage enough to keep them distorting the cooling tube arrangement. So here's the test shaft after we drove the casing. The one on the left, I just put this here, that's at low tide. And then the one on the right is at high tide. So we designed the top of the shaft a foot below grade. And you can see that was about 5 feet below the water at high tide. So we had to have the casing up high enough to keep our head on our slurry. Made it very difficult to construct since we had to set the steel down 10 feet below the top of the slurry. Disconnected, and we had to have the cooling tubes up, we had to have all the instrumentation for the sail to get over the top, but we didn't work through all that. Here's some pictures of the sail being built. The center section, I noticed David said that we didn't cool the bottom of the shaft, we may not have, I couldn't remember, David, but I know we ran the tubes there. You can see this is the bottom of the shaft, those are cooling tubes going through the sail. We may have some problem figuring out how we're gonna break plane those when we do the test. I don't remember how that was kind of blocked from my memory, like most of this test shaft. And then this picture here, you can see we had tip wires, we had the normal thermal integrity testing, but we also, the state wanted to verify everything. So I think we ended up with whatever, 19 tip wires or 20 tip wires in this test shaft to go along with everything else. So that just shows you kind of the scope of what we had to deal with. And then you can see that the CSL tubes and cooling tubes are extending well beyond the end of the shaft, which made picking the casing rather difficult. Here's a picture of our lifting frame we used. There again, we had this simple idea of a lifting frame, like I'm sure many of you use, so we could pick it on the end and pick your spill out. Well, when the engineer got through it with the weight, they determined that we needed a sled that weighed almost 30,000 pounds. And we couldn't pick it from the end, as you see there. So everything had to be stressful. We're having to pick from here and swing this stuff through. I think we probably should have done that easier, but we made it hard on ourselves. And what actually happened on the test shaft, we came in at 5 o'clock in the morning, we cleaned the shaft, and it was 4 o'clock before we were ready for concrete. By the time we got the steel up and dealt with all of the things you deal with on a wholesale, on the day of the pour, you got like 30 people show up you've never seen before. Everybody wants to see the pour, and everybody's in the way, and I was stressed out. And then I'm patient, and you know, I'm very anxious, kind of ADD, stressed out kind of person. I wore that barge out walking back and forth. The concrete company's waiting. We finally get the steel in place, we're ready for concrete. A temporary batch plant was built months prior because we thought the job was going to start in the fall. The hoppers had been full, and the humidity in the south, fly ash had chunks in it that wouldn't feed. They couldn't get concrete out of the plant. I mean, so we actually walked off the job at 10:30 that night. It took 5.5 hours to pour 235 yards or whatever it was, but the trucks were coming in about 2 an hour. And all I can see being a really small business is this $500,000 piece of steel here with all this testing and wiring and all that in there, and how I'm gonna pay for that when we lose this shaft. But here's some pictures of the actual testing. You'll notice the wind screen on the back there. David and I were talking about it earlier. This was the windiest place on earth. It seemed like the wind blew 4 out of 5 days at 25 or 30 miles an hour. So, but anyway, the testing went well. Even though the shaft took forever, everything came out good. CSL results look good. David will talk about the thermal testing later on that he did on that shaft and how we went forward with that. But in the end, after all my worrying, it all worked out like it was supposed to. But that was probably the most stressful day of my entire 61 years or 60.5 years on this earth. That was a hard day. And I will say, Dave and I were talking earlier, we just met each other. So Dave and I become friends over time. We spent a lot of time down there, but GRL came, Scott's people were there, they're filming everything and all of this. Like I said, it took forever to get the steel in the hole. The sail wanted to fall when we tried to cut it. Then the concrete plant stopped up. Then, after all this, it's getting dark now, I wanna start pouring. I've got 2 trucks and I start pouring and I look and the testing guy's got the chute, and I haven't even cleared the trimming yet. And he's pulled the chute of the pump truck over the wheelbarrow. And, I did what my guys call a bullet Johnny, I don't know. My wife says I have a flip out, but anyway, I lost it. I think they had to delete about 15 or 20 minutes of the GRL video. And actually, I begged them, please not put that on there, because I use words I didn't use. And yeah, I was very embarrassed the next day. Actually, I couldn't talk the next day, I was hoarse because I was hollering so loud at the inspector. It actually turned out to be David Works with ICE, who was a wonderful guy. He was really good on the job, and I really felt bad about that, but all that stress built up and I just lost it all. And like I said, that was like the second day David ever met me. I really think if I got rid of this guy for a year, we're gonna have trouble. So, anyway, we got the test shaft installed. And I'm gonna talk a little bit about the production shaft challenges that we dealt with there.
John,
Again, that's our one famous.
How supportive was your brother Don?
Don is very supportive. He was in bed while I was finishing that test.
As our only employee over here, Matt says, I'm not likable, so.
In all honesty, I did call him every 20 minutes to make sure he was as concerned as I was. I wanted to make sure that he couldn't rest, because that was quite stressful with so many things that we had never done before. Also, one thing I will go back up and say, with the test shaft, we assumed that in the production, we would not be able to complete these shafts in the time frame that the DOT typically allows. So you generally have 12 hours after you complete the shaft, you have 4 hours after you set the steel and place concrete. We knew that was probably going to be impossible once we got out in this channel, the access. So we actually finished the drill shaft the day before, about 2 o'clock. And we let the shaft sit. We were trying to get the DOT and everyone comfortable with the settling process of the power. We let the shaft sit. We came in and did a final clean out at 5 the next morning, but there was really nothing there. And we did start to pour till 4, even though we intended to start a little earlier. We did want to put a time frame in there when we would have more time. We could make a case for more time on the production shaft because we knew we were going to need it. Like I said again, there's our one famous picture. You can see all Brett's cases standing up out through there. He said he's going to do some advertising with that. I guess it's going to clear it up. But anyway, once we got going, you can see they were worried about us holding them up. That didn't happen. But after we finished the test shaft, there was problems. I don't know if it was the Corps, Coast Guard. I mean, there was 100 people involved. But getting the permits for construction was delayed quite a bit. So we poured the test shaft at the end of February. I think we poured on the 3rd of March. They didn't get the approval to put the access in until July. So our equipment was sitting there and all that casing was sitting in Brett Yard, taking up a lot of space. And he was calling me saying, I just can't, you gotta get the stuff out of my way, and I didn't know what to do, and they would put it, but, so we didn't actually start production until August. These pictures are under the access bullet, but actually the picture of the causeway is right before the hurricane. When it's actually empty, but you can see how narrow, it was just one mat wide, all the way up to the channel. And for most of the project, there was 4 cranes sitting on that causeway working as UIG had 4 or 5 crews building the rest of the bridge back here. So there wasn't access to get things by. And that's what I was talking about with like delivery casings. Brett had to get permits for 3 states and try to get this stuff here at like whatever, 10 o'clock. We're gonna open the causeway for me to get a piece of casing out. So.
Some of those drivers never drove again after that.
Yeah, and his driver's.
I don't know what y'all did to him on
They said it was dangerous. They didn't like floating on the causeway like delivery cases. Yeah, they did back out on us a little bit. I think we ended up having to deliver the last few to the yard and put them up. Anyway, there we are, loaded up on the barge. We started on bed 8, which was relatively simple because it was the end of the causeway. we could get the pump and the concrete down to access. Even though we were floating, we poured a second shaft on Pin 8 on August the 28th. September the 1st was when Henry McMaster evacuated the South Carolina coast for Hurricane Dorian, which was reached a category 5. I don't know if you remember, but it did a lot of damage to the Bahamas. It was the strongest storm ever recorded in the Bahamas there. Winds up to 220 miles an hour at one time. And while we were pouring the last shaft, they were tidying things up for a hurricane, which was supposed to cross the middle of Florida, and we thought we'd be in the outskirts. By the time we poured the shaft, the track had changed, and they had it dead center for Beaufort as a category 4, coming right over the top of the job. And so, anyway, this picture is not actually a hurricane, that's just an everyday picture, but I put it there. It looks like a hurricane. That's kind of what we dealt with every day, and you can see the rebars not really staying out of the salt. So the picture on the right is from my windshield, so right before we left after the hurricane. So everything's evacuated, and then they call us and say, we don't think we're safe enough, we're gonna move the cranes to a safe harbor, and we're just gonna leave your rig sitting out there, we think it'll be okay. And I'm like, H, no, if you know it was a brand new rig, you drilled 2 shafts. So I call a couple of guys, we ride back down and actually get the thing off the barge. We bring it to what little bit of landing area there was where they started the dirt work. We're still about 4 feet below the road, which overtopped during Hurricane Michael. Probably wasn't a safe spot. But I get in the truck, actually, when I was taking this picture out of the windshield, I called our insurance guy, and I was like, he'd been calling, because we had to do video surveys for the Coast Guard and all kind of documentation, because we assumed there was gonna be loss. And I said, well, you've managed to get the machine off the barge, it's not floating now, it's on the land. He said, well, I guess that's good news, but if you lose the rig floating, that's a $25,000 deductible, but if it flood on the land, that's a $100,000 deductible. And so, I started driving back out there. But we did. So, I guess as they were talking about earlier, I'll go back, when we were talking about earlier about check your insurance. So I said, look, you brought that up. So if I'd known our insurance better, I would have left it out there. This is a video, one of the UIG engineers had a house there, and he stayed. This is a video he sent. We were lucky that the hurricane actually came right toward Beaufort, went out, and it actually bobbled out about 75 miles offshore right in front of us. They did clock 100-mile-an-hour winds. We had a lot of seaweed and a lot of salt.
There's the rig.
There's the rig. And this is stuff stored up. But I was sitting home on Pins and Needles watching the Weather Channel 24 hours a day. And but he sent us this right after the storm started to move away. You can see maybe poles or whatnot. But all in all, it wasn't damage. We didn't have any damage other than, like I said, seaweed and salt. We did have about a 5-week delay, so somehow we managed to empty the whole job site and save it up in 4 or 5 days. It took almost 4 weeks to get it back in place because we didn't know where we put anything. We just piled stuff everywhere. This is a picture of one of Brent's cases coming in here. I was talking about this may be the one the driver quit on. I don't know. Bringing that on the end. This is just a picture of the pans right in the swing bridge there. Looks like we're getting ready to pour. I see the pumps up and the platform up. But, the steel, like I said, was very big. It was 70,000-pound range, 115 feet long, and we had to build them on the causeway. There was no way to build them in the yard and transport them, so we had to build them one at a time, set one in the dedicated barge for the steel there, and then started running them. The top picture is how we got water out of our tanks. We need to replenish our freshwater tanks. We've got our tanker. Everything came by tug. The bottom one is the rack of steel coming out. This is just a picture of the one going in the hole. So the concreting issue is the other big issue we had. So we took the job. We didn't read the pre-bid documents, I guess. So I've learned a lot today. I should have known 2.5 years ago. Evidently, in the pre-bid documents, it was stated that you wouldn't be able to overload this 26-ton bridge. So we get there, we're thinking we'll be able to do some engineering studies and say the bridge will hold it, and we'll be able to get concrete. Well, that wouldn't fly, because it was in the pre-bid documents, and everybody bid on the same thing, that no matter how many engineers looked at it, and they even offered to go in and dry pile and shore the old bridge, because United had the same issue with trying to get to the other side of the bridge. Couldn't get pile or anything across this bridge. Concrete, they had to do the initial dirt work with small excavators, small dozers, stuff they could get across the bridge. But anyway, they did finally allow, after weighing every concrete truck and doing all the calculations, allow us to use 6-yard loads on the bridge. Now this really made sense because I can have 8 6-yard loads out there, but I couldn't have 1 10-yard load. But anyway, as long as I stayed under 26 tons, it didn't matter if I had 100 of them, I was okay. That's the way it worked. And this is a picture of our little chip there, bringing out the concrete truck. So like I said before, having to move all the pieces, we actually had to finish the shafts one afternoon. We would clean them. We would actually set the steel the afternoon before. And the other thing about the job was there was no night work. You'd turtles running into barges or whatever. Had to have an 8-hour downtime at night with no lights. So night work wasn't an option, which didn't bother me a lot. But anyway, so we would have to get everything set up the night before. You can see here a little contraption we set up to be able to get concrete off the bridge with 2 chutes. And then the biggest issue with that was 6-yard loads, is I needed 20 yards in this shaft before I could turn the pump off, to get my trimming pipe submerged. We had to get 4 trucks turned around. That bridge was so narrow, the concrete truck drivers could not open the door to get out of the truck. So it was a really labor-intensive operation. You can see there, a lot of guys, and then coordinating with mixed truck drivers to make that happen, to get the first 4 in. I think some of the pours were as many as 36 or 38 trucks, so 6-yard loads. But anyway, we made it work. If you'll notice there, that's almost flat. You see right there, tide still lacks some, so at high tide, we actually, our chutes, the concrete wouldn't flow. We had to run a lever out there and lock it up. And then the tide would go down, and then it gets like this, flows real well, almost too well. This is just another picture of one of the pours there. You can see the pump truck in the background. And then these are just some fun pictures. So sometimes waiting on concrete, we get the fish. You can see Larry over there with the sea trout. They were biting pretty well at times. This center picture is, there was a bald eagle that nested over there. We had to keep an eye on it. They paid some guy from somewhere in Auburn where they keep an eye on this guy. Make sure he didn't get anywhere near us. But he would sit on the very high pole. Every day we poured. I don't know, he's fascinated with the pouring operation. We actually took that picture through a sight level because it's so far away. So that doesn't look very good, but that was an iPhone through a sight level, which I guess is amazing he got it. And then on the right here is Fred. There were about 100 pelicans that roosted under the bridge every night. Most of them were standoffish, but we had one that made friends with us right off the bat. He would hang around on the turbidity curtain and get on the barge, and about halfway through, we found out he liked sardines and banana sausage. Whenever he would come, or he'd see us eating, he would come out on the barge. I would go back there and give him whatever I was eating that day. He was very appreciative. But anyway, that's what I had, and now David's gonna come up and share a little bit about the test. Thank you.
Hey, John, did you guys have any, like on the Bonner Bridge, there was a bunch of hoopla about them putting the Bonner Bridge up there, a bunch of environmental issues and how it was gonna hurt the environment and all that. Did you guys have to deal with any of that on this job? Any of any of the granolas?
Well, we have a lot of environmental restrictions as you do any time you're in marine life. This bridge, actually, they built this big massive structure for really 3 boats. I mean, it's the Gay Fish Company. If any of you seen Forrest Gump and you saw the part of the movie where he runs into the dock, that was the Gay Fish Company right there. Those shrimp boats come through this thing every day. And of course, there was some barge loads going up. This is the whole coastal waterway a little bit, but we didn't get a lot of interference. We had to watch the bald eagle. We had to watch them, have a manatee watch and some things like that. But there was more talk of people in the community that really wanted to maintain the old bridge for the aesthetics and, you know, the history. A lot of people didn't want to see that go. They didn't want the new bridge, so. All right,
Thanks.
anything else? Anything else?
Yeah, those two were arguing about who was smarter and who was taller and who had more hair, so they got me up here.
Yeah.
All the But I'm younger, so, you know, the hair is still there, but it, you know, this job probably lost me a couple, gave me a couple gray hairs. I think we got pregnant with my fourth child in the middle of it, so I don't know if that was a stress relief or a stress inducer, so. You know,
So we'll have another funny thing.
man, more fun pictures. There's some, you know.
The rain gear,
that's
trash
the
bags.
classic, you know, contractor rain gear. You know, you get that at Walmart or Tractor Supply or any place, you know. So yeah, this was, I guess, the first time I ever met John, and I was telling him beforehand that when I started off, you know, doing foundation testing, I was doing it all over the state. And, you know, sometimes they'd be good shafts, sometimes they'd be bad shafts, and I couldn't figure out, I'm like, I do 2 shafts in a week that were damn near in the same area, and I couldn't figure out why one was so good and one was so bad, and then 5 years into it, I figured out, I'm like, man, every time I feel like I get a perfect shaft, me and Sims is doing it, so I was real excited when I came out to the site, and luckily everybody's got their hard hat thing on, and I see John Sims, and I was like, that has to be one of the Sims of Lee and Sims, so, I didn't notice him yelling on that first day of the drill, of the test shaft, so he didn't scare me off, and yeah, we became pretty chummy together after walking all the way up there. So, like he said, this was one of the first shafts in South Carolina that they instituted this mass concrete kind of stipulation. Anytime the shaft is 6 feet or bigger and twice as long as it is wide, which is every shaft pretty much. It has to be limited to a maximum internal temperature of 160 degrees and a differential temperature from edge to center basically of 35 degrees. The 160 degrees is more of a function of trying to keep this crystalline formation to degrade, you know, the concrete. The differential is more of a block cube pour thing for foundations to make sure that you're not going to have cracking, especially above ground, where, you know, you could have chipping and therefore rebar showing. So not exactly applicable to a cylindrical pile, especially that's below ground, but that's what we were dealing with at that time. And luckily you know, we were working directly through SCDOT, and the SCDOT project manager was in constant communication with me about keeping to these limits, and we're both practical people, so we both understood pretty much off the bat that if we got to 160.1 degrees Fahrenheit, it wasn't like we were gonna call John up and say, hey, start taking out the shaft because you need to do a new one, you know, because your shaft is bad because it was over these temperatures. So same thing with the max differential. We had some, that's what was on paper, but we're practical people, so we had some wiggle room. So like John said, you know, I guess he originally thought that one single tube would do the trick, but eventually they came up with 6 sealed tubes. You can you know, see each one of them there, and then they were basically CSL tubes tied in a 6-foot or 2-foot array, 6 of them. They shove a PVC 1-inch tube down the middle, pump water down the bottom, water would flow up through the tube and pour out the top. An open system, so the water wasn't being collected and recirculated. And they did that for 48 hours. In order to measure usually the maximum temperature in the shaft happens right in the middle of the shaft, where that's the heat is the greatest. In this case, we're purposely cooling the middle of the shaft, so that's not where maximum temperature happens. And we also have to measure that point. Usually thermal measurements are where steel already is, around the perimeter of the cage. So an additional steel tube was tied 2.5 feet from the center, therefore 1/2 foot away from where those cooling tubes were. And that's where we put thermal wires to measure that gradient temperature or the center temperature or the maximum temperature. So center meaning center of maximum temperature, not center of actual shaft. So the tip wires, I don't know how much everybody knows about them, but they're wires, they're thermocouplers that are spaced every foot. They read the temperature every single foot of the shaft where that measurement point is. Every 10 minutes, 15 minutes, whatever you really set it for. Typically those are tied into the cage and are sacrificial, so you tie them in, you get all the measurements, they get really good measurements, and then they're embedded in concrete and you can't get them out. That can be quite expensive, especially since if you're using CSL as well, it's kind of a duplicate test. So the kind of cheaty way is to actually drop those wires down the tubes, and therefore the CSL tubes, and measure the temperature of the water that's being heated up. So, but on the test shaft, the sacrificial wires were tied in, and we tied those into 3 production shafts, as well as suspending them to get a good comparison of those 2 methods. Like I said, on all the shafts, we use the suspended wires, but on test shaft and 3 production shafts, we did the sacrificial as well. That was good news because typically when you think of an 8-foot shaft, you think of a big cage, and it's really easy to work around and tie your wires in. Not when you put 6 steel tubes in the middle and an extra tube. Not the most fun. The important thing to note is that ASTM does not recognize those suspended wires put in the tubes as an applicable method for tip for integrity testing, because the water and the way that the water was kind of flow with itself and mix does not give you very good high resolution of your temperatures being measured. However, for this job, the tip wires were primarily being used for the mass concrete portion, and CSL was performed on every single shaft like every other shaft in South Carolina was the true method for integrity testing. So I know that John said that the test shaft he was all worried about. From my perspective on the actual data, the test shaft looked absolutely perfect from a CSL standpoint and a tip standpoint. It's wonders what happens when, like he said, 30 engineers are out there nitpicking, every single thing. There's a lot of care that gets put into a test shaft, so they usually turn out to be pretty good looking, I've noticed, and I don't care who you say, you can always get hills along the coast as long as you tilt your camera correctly and take a picture, so make it look like like he said, the concrete pour, that was a long and exhausting day. Didn't stop the pour until about 9 p.m. So they didn't start cooling the shaft until the next morning, 24 hours in the day. I'll point out that this purple line, so all these colored lines are the wires around the perimeter of the shaft. This black is literally an average of all the perimeter ones. This purple line is that gradient, or that center one, trying to measure the maximum temperature. So we felt really good. I mean, the maximum temperature was only 146 degrees. That's well below the 160 degree limit, and we didn't even start the cooling until 12 hours after the pour. So we were pretty confident that this was, this was going to work. It was also consistent along the shaft. Max differential was, 27 degrees, but once again, starting that cooling so late, we thought, well, if we, on the production shaft, when we actually started on time, right after the pour, it'll cool down the center of the shaft and bring this point in, and the differential will even be lower than that. So, like I said, on a typical shaft, you've kind of got, the heat is being radiated out into the soil. The soil is pulling up heat from that concrete hydrating. Your maximum temperatures are happening right in the middle where it can't get that heat out. Heat generation is due to cement concrete, the actual content, the mix design, the volume. That's a big thing. You've got more diameter, more concrete, more heat, smaller diameter, smaller shaft. So there's where you find your necks and bulges. You know, it's based on cover, so as the cage shifts this way and that way, your wires are attached to the shaft cage. So if you get closer to the sidewall, your temperatures are cooler. If this side then gets closer, it's hotter temperature. And then the top and bottom kind of look a little funny because the heat's not only going out to the soil, it's going up or down. And it's time dependent. So you start off, concrete that's batch set, gets up to a maximum, and then it starts bleeding off into, and then it's no longer creating any chemical reaction. It's not creating heat anymore, and it starts cooling back off to kind of the environmental. So this is actually what was measured. So this is kind of in theory, what that bell curve looks like of the heat going across the shaft. This is what I actually measured on this, and I'll explain to you why it doesn't actually do this bell curve in just a second. The reason it doesn't do that is because I tied an extra wire with a 6-inch. I just had literally an extra wire sitting around and had an idea that I was like, oh my gosh, I can actually tie something across the shaft and actually measure what the temperatures are across the shaft instead of all at the exact same distance along the perimeter. This was the framing, the support that they use for those 6, tubes. So it gave me this bar to be able to tie a wire across the shaft. So that's why I don't get that bell curve, because I'm not actually going straight across the shaft. I'm kind of going from one end to the other, and towards the middle, I'm actually at the same kind of radius from the center the whole time. There's just a rotated view, and that's kind of a picture also. That support system was where they tied that extra tube for the gradient of the center measurement. This is the test shaft, and there was a lot of equipment in the shaft. So there's a lot of wires, a lot of stuff in the shaft, and as you can see, really super duper easy to move around, especially with those supports once again in the middle. So there's kind of some highlighted of where I did 3 levels of that. Just like I said, I had a 75-foot long extra wire that wasn't doing anything. It's in my office collecting dust, and I thought I'd put it to good use. So as soon as they turned the cooling, so that previous image where it kind of started looking like a bell curve was before they started cooling, because we had 12 hours that the shaft was just heating up, nothing cooling. As soon as they turned on that cooling water, the wires right next to it cooled down like crazy. And what was also interesting is I could then measure, well, that is pretty much exactly where we have our gradient tube, which is showing the maximum temperature that's actually occurring in the shaft. Sometimes it would be over in that pocket of kind of the supports, but it's relatively measuring where the maximum temperature is. And this is a different view, so instead of, this is at a specific time, and it's the temperature with depth, so in this case it's going across the depth. You can also set a depth and look at the way that the temperature is fluctuating with time, so this is where your concrete's heating up, and in this case, that's when the cooling wires were turned, or the cooling tubes were turned on, and then that's the point where the cooling tubes were turned off. So, and you can see cooling system at. So, this is what I call, in most cases where there actually is a test shaft, is the real test shaft is the first production, when everything's actually in, what the production is gonna be. There's not a million people standing out there. You've got all the scenarios and everything that's actually gonna happen. For the test shaft, that was done in winter-ish time. They also used, it was on the land side, so they used tap water from the hydrant to cool the shaft. Well, due to delays, our first shaft was August 24th. Yeah, it's always really nice and cool in the middle of August in South Carolina down by the coast. So hot days, concrete's hotter when it comes out, and also instead of using the tap water from hydrant, they're using the river water, which got up to 86 degrees. So The highest temperature in this case was much closer to that 160 degree, that 160 is right there. And this is where the trimming pipes, you can see the trimming pipes are cool in the middle of the shaft, and then all of a sudden you get down to the 10 feet, and all of a sudden the temperature shot up. As soon as I collected the data, I went over to United and I said, were your trimming pipes going all the way down to the bottom of the shaft? And he goes, I think they were. He walks over there and he measures them and he goes, oh, I didn't account for the 10 feet of stick up or something like that because the shafts were poured below the top of the casing. So I could see in the data right away that it didn't matter in this case. It was more just a funny, like, did you mess up a measurement somewhere? Because it sure doesn't seem like the bottom 10 feet are being cooled, and they added PVC for the next one and everything going forward. So, like I said, you know, for 4 of the total shafts on this project, we did both embedded and suspended wires. They had, you know, a really good, you know, comparison. One of these lines is, can't read anymore, but the blue line is probably an embedded one, so that's the gold standard, and the red line is the suspended one. So we got, you know, anywhere from good to great, you know, correlation between those two. Once again, for our purposes, that was good enough. If we were doing this for integrity testing, we would not fully rely on the suspended wires. You know, typically the suspended was a little bit higher, so the suspended might be slightly conservative, but for the purpose of mass concrete, it was good enough. So here's a view of the cooling system at work. This is 7 hours after the end of concreting, and basically right after they got done with pouring concrete, they started the cooling process. The purple line, which is the middle of the shaft, is above the perimeter. 2 days after cooling, so the end of cooling, they flip-flop in the center of the shaft is actually the coolest part. And this little animation kind of shows how the perimeter wires between at 7 hours and 40 hours are basically doing the exact same thing, and the middle of the shaft is being cooled to the other side. So it was quite efficient. Like I said, this is another way to view the cooling. You know, up top, you know, these are the perimeter wires. The wires are on the perimeter. The single line down the bottom, that's that one grading wire. You can see that at end of cooling, the perimeter wires don't really change much because they're not being influenced by those cooling tubes in the middle. However, you see right when they get done cooling, the center of the shaft kind of rebounds a little bit and then starts coming back down. This was near the bottom of the casing, so, you know, down by the berry strata. Above the mud line, this was in flowing water, so you can just see how much different this response is. And once again, the end of cooling, you can't really see the perimeter wires, that gradient wire. You can see where the slope changes, where it's changing the level that it's cooling / heating up. But it immediately keeps on going down. What was also cool is that even in these perimeter wires, you know, which are 8 inches away from the sidewall, you could see, you know, these little bumps that happened once it kind of got back to equilibrium. Those are the tide changes. So those are spaced out about every 12 hours from peak to peak as the tide's moving in and bringing in new cool water and moving back out. So you know, this was for shaft cooling. You know, we were all worried about, you know, the center of the shaft, you know, and this complex contractor's cooling system, but we forgot about nature's cooling system, which was the river. So most of these shafts, I'd say only the 2 most exterior, or the 2 endpoint bookmark shafts were pretty much in the mud line, and there was a couple feet or so of actual flowing or water around the concrete. All the other shafts pretty much had upwards of 25 to 30 feet of straight water until it hit the mud line. So, you know, directly after concreting, we did this, then all of a sudden that water is cooling down the perimeter of the shaft. You know, at some time, and then even towards the end, it's actually, the water is actually cooling off the perimeter of the shaft, or the interior of the shaft too, so. Yeah, that's at the very end, you know, multiple days after it had been recording, when everything's kind of come back to equilibrium. So that would be basically at the equilibrium of what the water temperature was at that time. And this is basically getting close to the equilibrium of what the soil wants to be. So, you know, remember we had that differential condition of 35 degrees. Well, we're thinking that meant difference between the interior of the shaft and the perimeter shaft, just from the concrete cooling system. But what we didn't think about was the fact that the water was gonna be cooling the perimeter of shaft. So I think at one point I joked with United, and I said, you did a really good job designing, you know, the interior cooling. Now you need to figure out some heated blanket or some way to keep the outside of the shaft warm, because based on this differential thing, I was like, and it was a joke because I knew there's nothing you can do about it, but it just was something that wasn't exactly considered, and said, how can you control a river that's moving along and cooling the outside of your shaft? So, you know, from one side of the shaft, you know, these are all around the perimeter, but you might have a difference of 5 degrees or 25 degrees from one side of the shaft on the perimeter to the other side of the shaft. And this resulted in some huge differentials when you looked at the lowest perimeter wire based on the gradient wire. There were some huge things. And my best guess at this, and this wouldn't flip back and forth as the tide moved. It's not like one side of the shaft would be cool and then 12 hours later the opposite side of the shaft would be cool. What I think was happening was whatever side the tide was pushing against at the very beginning when the temperatures were starting to heat up, that's the way the tide was going. So it was like fighting fire with a fire extinguisher. You started off with fire small. That small fire extinguisher does a lot. By the time the tide switched, it was pushing against this side of the shaft. Fire's raging too much, it doesn't matter how much that tide is pushing against it. So that was at least my theory of why we had these kind of odd temperature differentials, and sometimes it would be on one side of the shaft, the other side of the shaft, sometimes it wouldn't be at all, so maybe we'd pour that shaft during slack tide. Like John alluded to, it's not the typical concrete job. You know, I'm a geotechnical engineer, so you know a bunch of numbers, but you know I'm not a structural engineer. But I sure think that 2 6-yard trucks probably weighs more than 1 10-yard truck, like John alluded to. But what this resulted in was lots of trucks and long pours, which resulted in these really weird temperature profiles, because the concrete down here at the bottom of the shaft is 5 hours older than the concrete up here at the top of the shaft. So from a temperature standpoint, because everything's not heating up at the exact same, heating up at the same rate as it wants to from that concrete truck, but it doesn't care what the other concrete trucks are doing. So it resulted in some kind of weird looking things, and this is another photo to show that, yes, in fact, 2 trucks that have only 6 yards of concrete back to back, that are basically loading the exact same pier bridge deck on the whole thing. Probably heavier than 1 10-yard truck, but all those trucks also kind of resulted in sometimes these different hydrating, you know, these different responses of the temperatures mid shaft. So these kind of 2 lower areas of temperatures, you would think, well, that's less concrete, you know, that's bad. Not terrible. You know, and that resulted in, once again, these large differentials. However, that was actually just a delay in probably a couple of trucks that had a little bit more retarder or something like in it, and were hydrating a little slower. So you kind of had this response like that, where it looked like, oh my gosh, this concrete's not heating up, there must be a problem with this concrete. You give it a little bit of time and it heats up. Normally it was just delayed response. But that was exasperated by the fact that so many different trucks being put in each of these shafts, because they're big shafts, they're long shafts, and small trucks. We also had these sometimes unusual cases where, you know, in the middle of a shaft, the batch plans would switch. So they'd have a problem with one batch plant and they'd start batching out from another. And so all of a sudden you get these kind of weird, like, this is one supplier and this is the other supplier. Same kind of thing, so then you just have to know that, well, this is a different concrete company and this is a different concrete company. Eventually, you know, they'll basically do the same thing, but yes, some of this is alluding to is, and this is definitely a project that I've learned that just as a testing engineer, you know, I can test whatever I want, and if I keep my blinders on and I only look at the data that's being collected, I might have some different opinion about the shaft. But John and I, you know, I kept in the best communication I probably ever had with people on site to try to figure out what was actually going on with all these shafts. And that information and a lot of those things, you know, that communication doesn't whittle its way onto a drilled shaft, you know, installation record. But having that relationship with the people on site and just the word of mouth of saying, oh my gosh, yeah, well, we had a different concrete supplier, then all of a sudden the batch plant broke down and we had to get it from somewhere else. A lot of that communication, that informal communication can greatly help with how I'm looking at things as a testing engineer. So we're running out of steam on the presentation. And in this case, so this little wrinkle right here was when the cooling system shut off kind of momentarily. I was actually doing CSL, and all of a sudden I looked over and I was like, anybody notice that the cooling system, like, water's not pumping anymore? And then went over and, you know, I think I put running out of diesel, but I think it was just the tide went out and wherever they had their inlet was out of the water. So I recorded on my notes what time and what day that was, came back, checked the data, and lo and behold, right at the exact time point, I could see that the temperatures were starting to not cool anymore. They were starting to go back up because the shaft wasn't being cooled anymore. Yeah, this was not the easiest site to move around. Here's a picture of that big long trestle, or that construction trestle. That guy was lucky for getting his truck even that far that day, and then there's a crane, and then another crane, another crane. After the first time with me walking all of my equipment all the way down here, I thought, I can't do that anymore, so I bought myself a nice little red wagon. Put all my equipment on, which that first day, or the first couple of days, all the laborers and all the contractors gave me a bunch of trouble for it. And then after about the second or third time, I had a whole bunch of people hollering at me to see if there was any room under my little wagon, and they could throw something on there, where I got it from, how much it cost. So, you know, yeah, it's quite the shift of attitude out there on my little red wagon. Yeah, and then you got to the end of that trestle, and then you'd have to get on this tugboat that was properly named the Little Chit, C-H-I-T, you know. And then you know, ride your barge, your tug out, to get onto this little floating island platform. And then, if I was, you know, if they were back here drilling a new shaft, and I had to test one of these shafts, then I'd have to ride a man basket or get on a tugboat and get my little island out here on a platform. John had a couple pictures of me sitting up there in rain with my feet dangling off the end, trying to wait for my ride back home. So once I got out there, better hope that I had a couple waters, and I think the guys threw me some chips or something like that a couple times because I was just stuck up there and couldn't get down. So an extra slide, you know, because of the large cages, they actually didn't set the column cage at the same time as the drilled shaft cage. So they poured a second pour with the drilled shaft that was 10 or 15 feet long before then coming back and doing the column cage. So we also had to monitor during that second drilled shaft pour. I found a use for, this was right when, you know, at least Charleston is trying to phase out the single-use plastic bags. So I went to Walmart and got a super heavy-duty plastic bag that on it says should be used 150 times. And I thought, who in their right mind is using this plastic bag at the grocery store 150 times? thick plastic bag, so it worked really good for protecting, my wires from concrete force. The suspended wires, you know, they actually they're not manufactured to be reused, but they did really well. You know, we used 41 total wires to monitor all 19 shafts, 36 of them being sacrificial, where we'd actually use the suspended wires for a while, wait until they were on the last leg, then tie them into the cage and get some good data out of them. It was also a relief because doing those suspended wires meant that we didn't have to climb through this pain in the butt cage to tie wires with those. So, you know, my conclusions, you know, as far as the tip wires go, was that the suspended wires, you know, did a really good job to monitor the temperatures. The embedded wires weren't needed for our application. You know, the contractor's cooling system worked out really well for them once we got things figured out with the temperatures and the timing and stuff. The main thing was to start that cooling initially, kind of like my example of the fire extinguishers. You got to start fighting those temperatures that the shaft's going to be, concrete's going to be creating early on. The tidal / running water complicated things, especially with the temperature differential. You know, I spent a lot of time coming out here to collect data. At the time, that was basically the means that you had to pull the thermal data off these things. Now they have cloud-based data collection that could have both limited my time out there and it could have limited the cooling time in some cases, because I could have been checking the data, you know, more regularly, and I could call up the contractor and say, hey, I know it says that you gotta run it for 48 hours, but I'm looking at 30 hours and everything's cooled off, you can shut off the equipment, but at the time that wasn't available. And temperature is a very long word to repeat, temperature. And I'll add to this, like I said, that communication is wonderful, and you know, especially getting to know people, and like I said, having that direct line of communication. You know, right off the bat, I could tell, you know, I want a good shaft. I'm the state's representative. I want to have a good shaft, but these guys, they also want to have a good shaft. So us working together and communicating, you know, we're all ultimately trying to get to the end goal. I'm not trying to hold him up. He's not trying to hold me back, you know. So that's it. These are, you know, my funny pictures from the actual job site one day. I don't know, I guess an inspirational day, and thought, well, I can take a bunch of funny pictures of me with questioning looks, and came home and showed my kids, and they all laughed and said I should use that somewhere on my presentation. So that's what I got. Any questions? Anybody got for me? I think
Was any shafts not cooled and tested to see if those tubes were actually working? I know you didn't see it.
no. No.
Were they?
No.
If there was no cooling tube, were they 170?
No, because that would have been a terrible answer to then try to say, okay, crap, now is the shaft good, so. So, no, everything was cool.
So we don't know if it was actually.
We don't, although, even with that cooling system, temperature relatively close to that 160 degrees. There wasn't a lot of care put into I know that if you batch concrete out at a much lower temperature, that kind of can solve your problem. Having that internal cooling system, that was less of a concern, especially with where concrete was being batched out and have ice plants. I think they tried to ice some trucks down, but based on the temperatures coming out there, it sure didn't look like they weren't massively icing the concrete down.
90-degree limit with cooling. Try without cooling, we had to try to put the 75.
Yeah.
It's not gonna happen.
Yeah, so with the
One
cooling,
of the things
we're
to me,
comfortably close to that.
it seemed like
limit that
everybody who wanted to
with the
store,
cooling.
where in the past, you drive on
With-
ice, okay?
With the
And they
temperatures
didn't
that
want
the
it to
concrete
work,
was.
they didn't
was
want,
being
they didn't want
batched
you to
out.
take and get the bearing that you were getting, because they wanted to
Yeah,
do so
yeah,
much and everything.
so it's still kind of being, you know, tossed around a
Especially
little bit,
SRE.
especially South Carolina.
One time,
hopefully at least that
I
differential.
took an
kind of
invoice in and I threw it on John Brown's
goes away.
desk. And I said, here. I said, how about buying me this
Yeah.
pickup? I said, that's what your fucking inspector cost me on the last job. Once I hit it.
Yeah, yeah.
A couple more times. And you hit it. I just hit a couple more times. And just lost time.
Yeah, so this was, well, I guess the cooling tubes and so it's still relatively small in the grand scheme of things.
What I missed.
I look at it more as,
How did you
I
guys
always
hear
think
it was
of, you know,
spoiled?
half the time that you have a problem.
Did it emerge?
More often
When you're
than
trying
not,
to shaft?
concrete flow
I think you
issue.
kinda glossed over that part. Yeah.
South
Get
Carolina,
Johnny to
that
explain
had
the handle.
seismic hazard, we already got a bunch of steel in the
That's
shaft,
the question too.
not allowing concrete flow.
So I did miss
Oh,
it.
good, now we've added.
Yeah, there was a
6
little in there, but
little
I
shaft
think he
that-
kinda
to
breezed
allow
right
concrete
past it.
flow the way it naturally wants to, so it's maybe solving one problem, this whole, you know, limiting the temperatures, but it's creating a flow problem with concrete, so, you know, this is not me standing here saying that I think every single shaft should be cool. This was a cool project to do, but I wouldn't mind not necessarily doing this. I like the tin testing, so if you got around the perimeter with it, it's already steel.
Hey, John, I missed the part, how did you handle the spoils?
We actually had a ocean going barge instead of the two small pans. We've been filling one barge and dumping one with crane. I don't think there's a picture of the dumping I had. But yeah, we had a barge. We actually hold 2 shafts worth of spoils at a time.
And then could you take it out and dump it, or did you have to unload
We
it?
had an excavator on that barge, so we'd have to take it to the bulkhead and use the excavator with other dump trucks and haul it off, which it was a 15-hour deal off the barge, 16 hours, so. Yeah, all those things kind of took time, but once we got the job running pretty smooth, we were able to get a shaft per week last,
Yeah.
probably 12 shafts, once we figured out the movement of the barges and how to make things work. It took us a long time to do the first one.
Yeah, yeah.
We were very slow.
Well, it was like I said, it was logistically a complicated project, so.
Was Don much help?
Hey, remember, I'm the Ravens
Well, he did come out and take some pictures.
He didn't get out of his truck, but he took pictures.
He was drove over, took some pictures.
But they didn't recognize him on the job site, right? They said, who was this random guy? And he said, wait a minute, that's my brother, don't run off.
Yeah, go to that last slide in their deck and I was actually with them that day, yeah. There's Don and Johnny.
I was out there making sure they were doing everything right.
And Johnny's the thinker up there in the upper left. He's looking out over the site thinking. He did that a lot.
I thought that was the two, that's not.
I'm doing this, so every time I'm thinking I'm doing this, I saw my granddaughter. When I go to house, she goes, are you thinking, Papa?
Looks like the one on the right, Johnny's trying to explain something to Don. Don's looking at him like, are you sure about that?
I was like, I'm a foot taller.
Oh,
And I said, no, we're taking a picture of this standing on the mat there, we can take it. Yeah, it was difficult at most times, I can tell you that the tops of the casings were about 12 feet above the bars, at low tide. So I was standing on the very top of the ladder, my little alligator arms trying to measure things, and then the tide would come up and you had to worry about fall protection, so.
Yeah,
It's
seven.
pretty drastic tide.
Yeah, 7 foot tide.
I think the king tides, we got 9 foot, wind phase, so yeah. It was fun, it was actually a fun project, now that it's over, it's very fun.
yeah.